Okay. So 36, you said? Positive, negative coterminal angles. So remember, when you're doing positive, negative coterminal angles, you've got 55 degrees. Okay. Now I'm going to do this in long form. I'm going to write it all out. I'm going to draw my angle. I'm going to place it, see where it's at, and then talk via how things work. Okay. So 55 degrees puts you first quadrant up here, like that. Okay. Anytime you place an angle in the first quadrant, that angle is itself its own reference angle. That's the only quadrant that happens. All right. So it's 55 degrees off the x-axis, so it's still 55 degrees. No big deal. Okay. Now, what I want to do is find the next positive coterminal angle with it, which means I need to spin and wind up in the same exact position. So if I spin to get to the same spot, I basically went 360 degrees plus 55.
Okay, so I was on the x-axis. I wasn't going all the way, but I had...
Okay. Now to go to the negative, you just go the other direction. And now this is kind of why I like to use reference angles a lot of times, because I know that if I went all the way around, I'd go 360 degrees negative. But I didn't go all the way there. I stopped 55 degrees short. So it would have been 360. I would take 55, subtract the 360, or just back it out and know that the other one would have been at negative 305. Okay? That's how that works when you're dealing with it with the degree stuff. All right? Yeah.
Number 30.
Okay. I think I did that one earlier too. So, yes, negative 5 pi. Okay.
Is there no reference angle?
Remember what we called that if you wound up on an axis? What do we call that?
Quadrantic.
Quadrantal. Yeah, it's a quadrantal. Okay. So, if you think about this in terms of the pi, if you think about it and counting it where it's going to wind up, all we have to do is count pi's. So 1 full revolution is 2 pi, which means half a revolution is 1 pi. So we count. Ready? 1 little, 2 little, 3 little pi's, 4 little, 5 little. So we stop there. Now, that's all we have to do. There is no reference angle when you're on a quadrantal because there's something very important that happens there that we talk about tomorrow. Okay? Yes, sir.
How do you know it's 2 pi?
2 pi is 1, yeah.
Pi is 2 pi is 1 full round.
Yeah.
That would be the circumference of the
Correct.
circle.
Yeah, 1 full revolution is 2 pi, half of it is 1 pi.
Wait, why would just like
Because that was a different problem. Yeah. Each problem is its own scenario. Don't try to pigeonhole it to the same thing every time. It's the concept I need you guys to remember. Okay. It's not factorization. It's 2.5. Right. 1 pi. If 1 full revolution is 2 pi, is it half a revolution 1?
Oh, okay, so it's half a revolution.
All right. What else we got? Which one? 38. What was yours? Oh, we'll come back to the beginning. It's 38, and I'll come back and answer that one. 38 says. Besides that. All right. So we got to do positive and negative coterminal at 420 degrees. So again, first thing we got to do is figure out where does it lie. Okay. So the easiest thing to do is we know that this is beyond 360. So if I go around 360 degrees, I know that I back that out. I have to figure out how many degrees are left. Well, I have 60 degrees left, which means that puts me first quadrant. Oops. That puts me at 60 degrees up. That means 420 degrees has a reference angle of 60. It's 60 degrees off the x-axis. Now, since we are beyond, our original angle is beyond 1 full revolution, I need to get the positive coterminal to be within 1 revolution. So in essence, what we've done is we've figured it out where it would land within 1 revolution, and the 60 degrees is positive. Okay? To get the negative, since I already have this drawn, this is why it's so important to draw these. If I go this direction, the full way around would have been 360, but I stopped 60 degrees short. So I stopped at 300, but I went the other direction, so it's negative 300. Yes, sir?
So if the original angle is within the revolution, do you need to find the positive coterminal?
Yes, because then you just add 360. So if your original angle was 100, your coterminal would have been 460.
Okay, but that would make it greater. Okay.
But that's it's the way it is. Yeah, but that's how these things are set up. If you're within one revolution to start, you add and subtract 360 or 2 pi. If you're beyond it to start, you bring it back in to get either, because if this was negative 420, my first negative coterminal would have been negative 60, and then it would have been positive 300. So it's the same basic scenario. Okay. Yes, sir? Just means to go in the other direction. Coterminal. Means the same exact thing. It's just a different direction. Okay. Just like. What's that? Yeah. Yeah. There's no other name for it. It's still coterminal. It's just going the other direction. Okay. Yes, sir. I didn't get rid of it because when I go in the other direction, I know that the angle has to be 60 degrees off of 360. So if I go in this direction instead of going the full way around at negative 360, I had to stop 60 degrees short. What's 60 degrees short? What was your question again? Guys, hold on. Oh, okay. So the question is about how do you know which one you're doing for degrees, radians, to degrees. So what's nice about that is that if you have an angle, let's see, let's just look at this row. If it says rewrite degrees to radians or radians to degrees, if your given angle has a degree symbol, you switch it to radians. If your given angle has a pi, you switch it to degrees. Radians have pi, degrees have the degree symbol.
And pi's on top, you put a pi on top,
Right.
and then if there's no pi on top, you put a pi on top.
Yep. So if I wanted to do 160, I have to since it's 160 degrees, to convert that to radians, I multiply that by pi over 180. And then I have to simplify my fractions. Now, simplifying the fractions, remember, you don't get calculators for this. Zeros, and then 16 and 18 are both divisible by 2. So you'd wind up with 8 pi over 9. Okay. Same idea if I have 400. If I do the 400, again, I multiply it by pi over 180, drop a 0. 18 and 40, again, if I just do them both by 2, I get 20 and 9 again, so I get 20 pi over 9. All right? To go the other direction, if it has a pi in it to start, that means you got to get rid of the pi. So if the pi is in the numerator, you know the pi has to be in the denominator. The other thing is always going to be 180. So the pi's drop, 0, 0, you get 18. Okay. Lots of quick fraction stuff. Okay. And then the last one, I'll get you in 1 second, Mike. Then the last one, again, since it's negative, it's still going to be in negative degrees because it's going the other direction. You just multiply it by the 180 over the pi. Pi's drop. 6 goes into 18 3 times, add a 0, you get 30 times 15, you get negative 150.
I was just gonna say, like, can you just like see pi as 150 because it's half circles? So you just like 180 divided by 10.
Yeah, that's in essence what we're doing, yeah. Bless you, because pi simplify out. Bless you. 6 goes into 18 3 times, add a 0, so it's 30, 30 times 5 is 150. Bless you. Michael, do you have a question?
Yes, good question on number 40.
All right, so let's look at it. 40 is a positive, negative coterminal. This one is beyond one full revolution. So anytime that I have beyond one revolution and I have top-heavy fractions, this is the time and the place that I say that mixed numbers are your best friend. Okay? Normally I say mixed numbers suck because they don't help you with anything. They help you a lot here. Does it start to make sense why I say this is the best place ever invented for mixed numbers?
Go round and round.
You go round and round, and where it stops, nobody knows. So 2 goes into 13 how many times? Now, I think somebody in here earlier was saying, can you write it as 6 pi and 1/2 pi? Absolutely. It helps you keep it straight as you're going through, okay? So now what I want to do is just place it and figure out where I'm at. So 6 pi, if you want to count it and have fun, we go 1 little, 2 little, 3 little, come on! Ready? 1 little, 2 little, 3 little pies, 4 little, 5 little, 6 little pies. So there's our 6 pi, all right? What's left over? Where does that go? On the thing. The thing is called a
Y-axis.
quadrantal angle. Anyway, so now when we place that one, if you had to figure out the positive coterminal, this was beyond one revolution 3 times. So you had to back out 2 pi to get 4 pi. Back it out again. Back it out again. When you backed it all out, you wound up at pi over 2. There's your positive coterminal angle. Because now that leftover is within 1 revolution. You always back out if you're beyond one revolution, until you get within 1 revolution. Okay? Now, yes, sir?
When you're backing up, if you see that it's like a number.
It's fine, absolutely. Okay? Absolutely. There's nothing wrong with that.
When we're given it in ratings, do you want the answer in ratings?
Yes. If it gives ratings, you stay ratings. If it gives degrees, you stay degrees. That's never switch between. Okay, never switch between. Kevin.
Okay, so like for this angle, it's basically the coterminal if it's more than 1 revolution.
Depends on where you're at. Okay. This is a quadrantal angle. It doesn't have a reference because it's on an axis.
It is its own reference.
Not necessarily. It's on an axis. It's a quadrantal. It's different. There's a lot of weirdness that goes on there. Okay. The only thing you want to think of it if you're your own reference angle is if you're first quadrant. If you're second quadrant, 100 degrees isn't a reference angle. 100 degrees is 80 off the x-axis. Okay. Yes, sir.
I thought you called it a quadrantic yesterday. Is it quadrantic?
It's quadrantal. Quadratic. Hey, we'll do quadratic for trig functions too, just so you know. Anyway, so this was our positive. I gotta do my negative. I'll come back. So I go this direction. Negative 3 pi. Yes, sir. There's something fancy that happens there. We'll talk about it tomorrow. There's something. This is. It basically boils down to. Notice how? Remember last year and in this year, we never trigged with 90-degree angles. We never used the 90-degree angles as part of our opposites and adjacents and all that. We never placed ourselves at that angle. There's a lot of weirdness that happens there, and we'll talk about it tomorrow. Yes, ma'am. Yep, that's all it is. And it works the same way if it was negative. You would just basically be adding 2 pi all the way up until you get within 1 revolution. Your first coterminal angle could be negative, and then the next one would be positive. It works the exact same way. All right? Yes, ma'am. 42. What is it? What does it say? What's the angle? 24 pi over 7? Okay.
So 3 and 3/7.
So here, again, what we always do is we always want to look at in terms of a mixed number, so it's easier to count it. 7 goes into 24 3 times, so we have 3 and 3/7 pi. All right? So we try to place it from here. When we place it, it's positive, so we have to spin around. Ready? 1 little, 2 little, 3 little pies. Now, I've got my, I got the 3 parts done. 3 over 7. Is 3 more or less than half of 7? Less than 7. Use that idea of breaking the fraction down because you know that halfway would have been here. So it's got to be less than halfway. So we know it's going to drop into the 3rd quadrant. We know that the reference angle is 3 pi over 7 because that's how much further we drop down. You okay with me on that? Mm-hmm. Okay. Now this one was beyond 1 full revolution. Is it beyond 2 revolutions?
Yes.
No.
No.
If it was beyond 2 revolutions, it would have been 4 pi.
5
Okay.
pi, 6 pi, 7 pi.
Right. So now all I have to do is think about it in terms of to get the positive coterminal. If I start it here, there's 1 pi or 7 pi over 7, and I add 3 pi to it, and I get 10 pi over 7. Okay? To go negative, starting at 0 to negative 7 pi over 7, I'm keeping that same denominator, I stopped 3/7 before that. So it would have been 4. Is it starting to make sense why it is so important to understand how far you are off the x-axis? Because that's how we count everything.
For the positive one, is it okay if we just go like 1, 3 pi over 7?
That's fine. I have a habit, I always go back to, I only use the mixed number to count as I'm placing. I understand because you can just do it, let's just take out 2, it's 1 3/7. It's fine. I'm more of a custom, I'll always write it as the topic at that point because I don't want to keep the denominators. Okay. Starting at 0, 1 pi at 3/7. I'm talking in terms of sevenths. So 1 pi would be 7 pi over 7 at 3. Okay, that's what it goes. Sir?
So like, what are we gonna do?
What do you mean?
Like, cause finding angles and like the coterminals and whatnot, like, what are we gonna do?
Well,
Supper.
Do I have this one open still?
How many tabs do you, or windows do you have open?
A lot. Because that's just
How do
what
you
it
keep track of them?
Everything's labeled.
No, we're 90% of we now know why your computer crashes so often.
It doesn't crash that often.
I feel bad for it. Like, think it has building crash, and I think that's oh, that's oh yeah, this comes in handy. Yeah, I just I don't know what that laugh was. No. Is Cal?
Because what'll happen is eventually, you don't write this down, don't write this down. Eventually, probably a couple weeks maybe? I don't know. I don't know if we'll get this before spring break or not. Eventually, we'll be able to figure this out, solve the theta. What theta values give me this as a true statement? Now, in order to be able to do that, you have to know how to work with identities. You have to know how to work with a bunch of stuff. I also have to know that cosine squared is the same thing as saying 1 minus sine squared.
Oh yeah.
No.
Wait, how is it 1 minus? It has to do with the units.
Right. What's that? Yep.
No.
So hold on. Which means I got to move everything to the right. So I get 2 sine squared plus sine theta. The other 2's drop out. I can factor this out. I have sine equal to 0, don't I?
Yes.
When you had quadratics, you had 2 parts equal to 0. It means you set both parts equal to 0, correct? So what angle has a sine value that's equal to 0? What angle has a sine value that's equal to negative 1/2? To be able to do that, you have to understand where does it work. Nope.
So we're not
And you have to
finding.
make yourself make it go.
So we're not finding
So
the specific number.
We are.
But
We are.
Sine.
It's okay. We haven't gotten there yet. So the whole idea of why are we able to set these things through? Why are we setting these things through is because eventually when we learn how to place this value, what does it mean to be negative 1/2 in terms of the sine value? What is all that equal in terms of where is it placed and how far the degrees or how far the radians are off of an axis? Give you the values so that way you can solve the equations to go up there. But in order to be able to do all that, we start with this. Yes, sir?
I just want to ask a question. When it says sine squared, when it says sine squared theta, what is the square term attached?
Sine.
It's attached to the sine, right?
Yep, and we'll talk all about it. We got a little bit. We won't get to the identity portion of this until not next week, but the following week we'll start doing identities. Okay, we'll do identities the following week. You guys can get really, really pissed off at some of those guys. So it's fine. 4 weeks, 3.5 weeks. So the last little bit of this section then goes into something you guys did last year. And it deals with arc lengths and areas of sectors. Last year, you guys did arc length, you guys did area of a sector. I briefly showed you guys yesterday how arc length worked. If you guys remember when you guys did arc length last year, you dealt with the circle. You had to have some central angle, and you're looking for the distance on the actual circumference. You guys learned that as central angle over 360, stop talking please, times 2 pi r. Yesterday, we converted that to show how degrees switch to radians. Last year, you guys were converting things into radians, you just didn't know that's what you were doing. Okay? This year when we're doing this, when we did our conversions, we just made our radius 1, so we just disregarded that. So what we did here, yesterday, we simplified this and said central angle over 180 times pi. That gave us radians. Okay? So now this is going to equal what we call theta. Central angles will be given to us in degrees. Theta is generally in radians. The way you can tell the difference is if there's a degree symbol, it's degrees. If there's a pi, it's radians. Okay? It's kind of an easy way to distinguish between the two. All right? So what will happen is that our arc length is just this formula. Theta times r, where theta is radians. Okay? So, excuse me. And then area of the sector, again, same idea. When you guys did that last year was what? Central angle over 360 times pi r squared. Well, now we simplify it through, and we get 1/2 radius times theta. Again, this arc length portion, there in the textbook they call it S, I think for a sum of the circumference. SOME. Sorry, it was really bad. I just thought of it. Anyway, so you wind up with these two very, very simple formulas. There's not much to this. What happens with this stuff, it winds up being a lot of simplifying of fractions. Okay? It is a lot of fraction simplifying. So, arc length is going to be radius times theta. Theta is in radians. That's the main thing. And the area of the sector, again, it's going to be 1/2 radians squared times theta, where theta is in radians. So you might do little conversions here and there. For example, if I have a radius of 4 and let's say a theta of, we'll say 45 degrees. Sorry, we'll do angle of 45 degrees. Make it easy to start with. And I want to do arc length and I want to do area. So arc length, we're going to do both with them, and then area. Okay. So arc length, first thing we gotta do is convert it to radians. So we know that if you wanted to write it out long form, it's gonna be angle over 180 times pi times r. Okay, that's how we know that's gonna work. The area of the sector would be, again, since we're starting with degrees, it would just be 1/2 angle over 180 times pi times r squared. Doesn't hurt if you write it out like that just to get yourself ahead of where it's going to go. Okay. Fill in the blanks. 45 over 180 times 4 times pi. If I double 45, what do I get? 90. If I double that, what do I get?
180.
So 45 is what of 1/4. Okay. So again, you wind up being able to simplify things through. You get 1/4. What's 1/4 of 4?
1.
So your arc length is pi. Okay. Yep, that's your answer. Now, area of the sector, same deal. We have 1/2 45 over 180 times 4 squared times pi. Well, we've already figured out that 45 over 180 was what? It was 1/4. Okay. So we have 1/2, 1/4, 16 pi. What's 1/2 times 1/4? 1/8. What's 16 over 8? 2. So your answer is 2 pi. It's all fraction work. Okay? All simplifying and working with your fractions. Right? This usually isn't so bad, except for the fractions can be kind of messy from time to time. What's up? Yeah. To this one?
Sorry.
My ham. My wife is so lucky, isn't she?
I can't believe how lucky she is.
I know.
It's insane.
She should, I mean, she is. She's not insane, but. Let's do the 15 and 175, because that's a weird one. Again, we'll do it again with, I wanted to give you some crummier numbers to show you guys that it's okay to learn how to work with fractions. Yeah, I don't know. Am I going to yell at you if you guys label your stuff? Yes.
Yes.
Well, you should.
I should, but I always forget. Arc length. Guys, come on. Arc length, again, you've got your central angle over 180 times radius times pi. Make a decision on how you want to simplify. I saw you start counting things. One of the things I know is that 15 goes into 180. Because 15 goes into 18 how many times? Once. How many are left over? 3. 15 goes into 30 how many times? 2. So the 15 and 180 becomes 12. 1 over 12. What's 1 plus 2? 3. What's 1 plus 7?
10.
I hope you find that calculator. Well, again, what's 1 plus 7? 8. What's 8 plus 5?
13.
Is 13 divisible by 3?
No.
No. So I know I can't simplify this any further. So my answer would be 175 pi over 12. You guys know that trick, right? Divisible by 3?
Yeah.
Add them to see if they're divisible out. So then I would be done with that. Okay? Yes, absolutely. Either place is fine. Okay? Either place is fine.
So do you, if you have a 4-digit number, can you add them to
Yeah. Mike, we got. Yeah.
On this one, why didn't you like
Because I saw 15, I knew 15 and 180 real fast. It was quicker. You can go the other way. It's pattern, if you recognize pattern. 15, what I want, think of it this way. 30 degrees goes into 180. If you think 30 goes into 18, how many times? 6. Is it 15 half of 30? So when you take twice as much to get into 18? Same right here. Okay. If I do the sector, if I do the area of the sector, again, it's my angle over 180. Then I have to go, sorry, I have to do 1/2. Then I have to do my radius squared, which was 15 squared, and then I got to put a pi in there. This one isn't as clean. Okay? This one won't be as clean. So now, excuse me, if I do the 5s with the 175 and the 180, if I start there, if I go 175 divide that by 5, 5 goes into 17 3 times, 2 left over, so I get 35. Okay. 5 goes into 18 3 times with 3 left over, so it'll be 36. Makes sense because they're just 5 digits away from one another. Okay. So I have 35 and 36. There's nothing that works there. I know that 15 squared is 225. Are you okay with that?
Yeah.
Okay. So let me rewrite. I have 1/2, 35, 36, 225, and a pi. So what's 3 plus 6? 9. 2 plus 2 plus 5. So they're both divisible by 3, but is it worth taking a shot to see if they're both divisible by 9? Is 36 divisible by 9? Okay, try it. Okay. Does 9 go into 22? 9 goes into 22 how many times? How many are left over?
4.
9 goes into 45 how many times? 5. So this becomes 4, and then what do we say? 25. Okay. So now doesn't look like anything else is simplifiable, is it? Nope. Now I have to multiply it out. So 2 times 4. Got a pi here. I just got to multiply 35 times 25. Okay. That's I was right. So it's what, 875? Yeah. There we go. Break it into smaller pieces as you're simplifying them out. If you had to go by 3s a bunch of times, it would have worked as well. But I saw that they both added to 9, so I thought I would try it. We got lucky. Yes, sir.
Why did you put 175 over 180?
Angle over 360. I'm sorry, angle over 180. That's the conversion from the degrees to the radians part there. Yes, sir.
So, before you multiply by the half, you can take the, whatever number
Nice.
and see if it'll
Yeah.
fly out.
Yeah, it doesn't hurt. I knew that when I first saw this, I saw 36 is divisible by 3, and I know 15 is divisible by 3.
So multiply out.
They're going to still be divisible. So that's why I thought I would check and see if it, because if 3 goes into 15 and 3 goes into 15 again, that means 3 and 3 it has to go 9, which means 9 would have to work. So you start playing around with the numbers, you kind of figure your way through it. Okay. The answer was 875 pi over 8. I multiplied the 35 times 25. That's what was left in my numerator here as we went through. Or was it supposed to be? Oh, was it 36?
No.
Oh, that was the one above it. I got lost in my own handwriting. Okay. So I made a little sheet here that has basically all this stuff on it, and it has way too many problems than what you need to really worry about.
Except you should do extra work like you say.
It does not hurt. It makes everything easier. The more practice you do on things, the better you get at it. Go figure.
Or just say you don't have
Now, obviously, this whole setup columns going all the way through. There's absolutely no reason for you to do every single one of these. I would just kind of pick a column and go through it. What I'll do, since this was one of those nice little CUDA sheets, when I post the PDF file, I'll have the last page that I did not add to yours with the solutions on it, so you can check it on the calendar. Okay, and then we'll go from there. Tomorrow we'll get into the how do we start working with the trig of specific angles, how we use reference angles to get there, what do quadrantals show us, and remember how we placed angles last week? We said the sine of theta was 3/5. What was the cosecant, or what was the tangent of that? We had to place stuff through. We'll start working with that stuff and going through all 6 trig values and all that as well. Question earlier was, when's our next quiz on all this stuff? My best guess as of right now would be next Friday. It's usually over these first 3 sections of non-calculator stuff as we go through. 13.2 takes a solid 2 days. That'll get us finished up by Monday. Tuesday, Wednesday, and Thursday of next week will probably be 13.3. With a little bit of review at the tail end of it, and that's another really good visual section, and then we'll throw the next quiz then on the following Friday. Then it gives us 2 weeks, I believe, before we go to spring break. My best guess, as of right now, I think there's a lot of people leaving on that Friday. If there's a banning thing, there's something else going on that Friday before spring break. So I'm going to shoot for having the test for everything on the Thursday before spring break. There will be 2 more sections before we get to the test. So the test will be all of the non-calculator stuff that we've done, which is basically 5 sections. As we get to it, and those 5 sections are going to take us over 4 weeks to get through. So if you think about how long it takes the material to build into. That's not what, next week is the first week of March. So it would be what? I think I have it on the calendar already. So, yeah, the week of the 9th, we'll probably be doing trig identities. That's like I showed that sine squared turned into 1 minus cosine squared. Why do all those work? Those take a good 3-4 days to go through. Then we'll start solving equations. Once we get to the equation part, equations go rather quickly because by then everything's beaten into your head about where certain things occur. So, like I was thinking, my best guess is we'll be testing out of all the this first portion of non-calculator trig that Thursday. And then when we come back from spring break, we'll have a week, probably 2 weeks of graphing of trig functions. Maybe only a week and a half to be able to finish that up. And then I think we've been kind of done with trig, and that puts us almost like 8 total weeks of doing it. So it's a good chunk. It goes by really fast. I love trig. What we got?